class last time. If you remember, we said that we might have some rigid body, and there might be some force acting on this rigid body at a point that might be over here. So we'll say that we have some force like this, and maybe for some reason we want to apply that force at a different point on the rigid body, but we still want the rigid body to behave in the exact same way as we would observe in this picture. So we said that what we can do is we can essentially apply two forces, same magnitude, equal and opposite directions at this new point. One of those forces would be representing the movement or the reapplication of this force to the new point, and then the original force plus the other one would form a force couple, which we could then create a force couple vector, moment vector, that would be at that point as well. And we ended up with a picture that looked like this. So we have here at the new point not only the force, but also some moment vector. Because we said if we change the point of application for that force, we're going to change the way it wants to make that rigid body rotate. The translation would still be the same. Okay? The body's still going to want to translate up and to the right, but the way it rotates will change based on where the force is applied. And I demonstrated with I think I used the eraser on the desk here and showed you, depending on where I apply the force, I get different kinds of rotation. So if we want to move the point where the force is applied, we have to add a moment vector to make sure the rotation that we see in this picture would still be the same as what we see in this picture. And so we did an example just like this at the end of class last time, where we had one force acting on a rigid body and we moved it to a different point, and we saw how we had to add a moment vector in to keep the rotation tendencies the same. Remember, this equal sign actually means two things here. This equal sign means that the sum of the forces in the left-hand picture has to be the same as the sum of the forces in the right-hand picture. And that's true for any direction, the x direction, the y direction, if it's three-dimensional, for the z direction as well. Also, the sum of the moments around any point in the left-hand picture has to be equal to the sum of all the moments around the same point in the right-hand picture. So you see these two conditions combined guarantee that the translation and the rotation of the rigid body is going to want to be the same in both cases. So what we want to do today is we want to extend this idea to rigid bodies that have more than one force acting on them. So what happens when we have a rigid body that has two or three or four, even more forces acting on it, and we want to come up with what we call an equivalent force couple system? So in other words, we're going to look at a situation that might be like this today. Let's say we've got our rigid body, and now instead of having one force act on that rigid body, let's say we have a whole system of forces. So maybe we have that force that we saw before, we'll call it F1, but in addition to that, maybe we have some force like this we'll call F2, maybe a force over here that we'll call F3, maybe some force like this that we'll call, I guess we're at F4 now, and then maybe some other force here, that's F5. Now you see that rigid body with those five forces acting on it, it's a little bit hard to just visualize how that rigid body is going to behave under that system of forces. But what we can do, using the idea that we introduced at the end of class last time, is we can just pick some point, maybe this one, and we can just move all five forces to that point. Now, as we saw with the example that we looked at last time, when we move a force, we have to add a moment vector in. So when I move F1 to this point, I'm going to have to add a moment vector in. When I move F2 to this point, I'm going to have to add another moment vector in. And same thing, when I move F3 to this point, I'll have to add a third moment vector in. So what's going to end up happening is I'm going to have five force vectors and five moment vectors all acting at this point. Now, because all five force vectors are acting at the same point, I can just add them up and find a resultant force. So we're going to get some resultant force here. That would be the sum of the five individual forces. And then I'm going to have some moment resultant that would be the sum of the 5 moment vectors that have to get added into the picture when we move each of the 5 forces. So now, I might not be able to see how the rigid body is going to want to behave under this system of 5 forces, but when I just see 1 force in 1 moment vector, then I have a better idea of how this might want to translate and rotate and behave. So that's really what we're going to do today. It's just repeating the process that we saw at the end of class last time, 2, 3, 4, or in a case like this, 5 times. And there's one other case that we might see as well. We can take this picture that's got the resultant force and the resultant moment vector, and we can find another point somewhere in the rigid body. Maybe it would be down here. And if we move the resultant force to this point, we're going to have to add another moment vector into the picture. Anytime we move a force's point of application, we have to add a moment vector in order to account for the change in the way the rigid body wants to rotate. Now, if we choose this point carefully, we might be able to locate this resultant force at such a point that the moment vector we would add in here would be equal and opposite to the moment vector that we had here. So what would happen? We get that moment vector plus the opposite of it that we would have to add into this picture, and net result is those two cancel and you don't see a moment vector anymore, because we chose this point carefully enough that just applying this force at this point will still cause the same rotation that we would have in this picture, where you've got the resultant at a different point and the moment vector in there. So we might be shown a system of forces like we have here in the extreme left-hand picture and be asked to find an equivalent force couple system. That means a force and a moment vector at some particular point. We might be asked to just take these 5 forces and find a resultant force and the point where it should be applied, so that this one force will have the exact same effect as all of these forces, as well as this equivalent force couple system. So we could be shown the left-hand picture and be asked to find either one of these, or maybe even both of these, right-hand pictures. We'll see that in the examples that we go through today. All right, so we'll do a couple of 2-dimensional problems, a couple of 3-dimensional problems, just to make sure we cover all our bases here. Okay, we'll start off with 3.85. Now, if you see 3.85, it's going to look like a 3-dimensional problem because you have this 3-dimensional box and you've got 3 different people pushing on the box. But if you are observant, you'll notice everything is happening in the XZ plane. So we really don't need to concern ourselves with what's happening in the Y direction here. So I'm going to treat this as a 2-dimensional problem since all the action is happening in the XZ plane. So if we were to take a bird's eye view here, if we were to be sitting on top of the Y-axis looking down on the top of this box, we would see something like this. So the box would be maybe like this, and the X and the Z axes, let's see, the X axis would be coming down this way, and the Z axis would be coming over this way. Okay, so if you just sat on top of the Y-axis and looked straight down, you would see the top of the box, and you have the X-axis and the Z-axis oriented like I've shown. And then the 4 corners on the box are labeled. This is A. Point B is equivalent to the origin here, and then C and D. And then 3 people are pushing on the box. Each one has a force. The person who's pushing at point A is pushing to the left with a force that has a magnitude of P. The person who's on the left side of the box is pushing towards the right with a force of 200 newtons. And then the other person who's pushing on the right edge of the box is pushing with 200 newtons to the right. Okay, so let me just give those two forces names just so that we have some way to refer to them. Let's call this one here F1, and let's call this one here F2, just so they have a name that we can refer to later. And a few dimensions that we might want to know. The box is 1 meter by 1 meter. And it looks like there's a distance of 0.2 meters for F1 and a distance of 0.7 meters for F2. Okay, so let's see what they ask us to do. Part A. Here they tell us to assume that P is equal to 240 newtons. They want us to replace these three forces with an equivalent force couple system at A. Okay, so right now we have the rigid body that has three forces acting on it. They want us to move all of the forces to the point A. And when we do that, of course, we're going to have to add moment vectors in. So what we're going to end up with is a picture where we have one force and one moment vector at the point A. And we want that force and that moment vector to be such that the picture, the box, will behave in the exact same way with that one force and one moment vector as it will when we have these three individual forces acting on it. So what I'm going to do is I'm going to set an equal sign here, and I'm going to draw the box again, and at the point A, I'm going to put a force in a couple, or a moment vector. So typically what I do is I show my force with an x and y component, or in this case it's going to be an x and a z component, and I like to show those acting in the positive direction. So given the orientation of the x and the z axes, I might actually put here, I have FAZ and FAX. And then I like to show some moment vector as well. So let me put here, I'll call this the moment around A. So FA is my force, that's going to represent my resultant force, and the moment around the point A is going to be my resultant moment vector. So what I'm going to do is I'm going to take all of these forces, one is already acting at the point A, so I really just have to worry about F1 and F2. I'm going to move them to the point A, add up all three forces, and then when I move those F1 and F2 forces, I had to put moment vectors in. Well, when I add those all up, I'll get my moment vector for A. Now, the way we actually go about finding the three pieces of the puzzle here that we need is to make use of that equal sign in between. Keeping in mind that tells us that the sum of the forces in any direction in the left-hand picture equals the sum of the forces in the same direction in the right-hand picture. So we might say this, we might say the sum of the forces in the x direction. Okay, so the x direction, positive x is going down. Nothing is going in the x direction in this picture. All the forces are horizontal, so they're all in the z direction. So I'm going to have 0 on the left-hand side equal to, in the x direction I have FAX on the right-hand side. So that just tells me that the x component of the force that will be at A is 0. And that should make sense because if you move all three forces to the point A, they're still all going to be horizontal forces, so you're not going to have anything in the x direction. In the z direction, now here's where all the action happens. In the left-hand picture, remember positive z is going towards the windows, so I have positive P minus F1 plus F2 equal to, I have FAZ in the positive Z direction here. So I plug the numbers in for P and for F1 and F2. Let's say this is going to be 240 minus 200 plus 200 equal to FAZ. So I have here FAZ equal to 240 newtons. So right now, I know what the force is that needs to act at the point A. If I just combine the two results that we found here, what this tells me is that FA, written as a force, has a full magnitude of 240 in the Z direction. Okay, so I might show 240 newtons going in the positive Z direction. That's only half the answer, because you see it says find an equivalent force coupled system. Well, we found the force, whose components we see here, FAX, FAZ. We know what the actual force is now. We have to find the other half of the solution, which is the moment vector. That's going to make sure that this crate rotates in the same way that these system of forces would want to make it rotate. So what do? I take the sum of the moments around some point. I pick any point that I want. The most convenient point that I can think of is A. So in the left-hand picture, let's assume that we're holding the point A fixed and we're pushing to the right with F1. That's going to want to generate clockwise rotation, so we're going to have a negative term here. So I put negative. The magnitude of the force is 200, and the perpendicular distance from the line of action to the point A is 0.2. So negative 200 times 0.2. Now hold the point A fixed and push towards the window with F2. That's going to want to knock this or spin this counterclockwise. So it's going to be a plus now. That magnitude is also 200, and this time the perpendicular distance from the line of action to the point A is 0.7. Now the force P does not have a moment around the point A because its line of action goes through the point A. If you did F times D for that force, you're going to get P times 0 because there's no distance between the line of action and the point A. So we talked about that before. Force will not create any rotation about a point that's on its line of action. So now in the right-hand picture, because we're choosing the point A as the point where we're taking the moments, FAX, FAZ create no moment because their lines of action go through the point A. But we do have the moment vector, MA. So we have MA equal to, we just run the numbers from the left-hand side of the equation here. Looks like we're going to get 100 if we do that, Newton meters. Now remember, moments are vectors, so we need to say here that the moment around A, positive 100 means the direction of rotation ends up being counterclockwise. Or more correctly, we should say it's consistent with what we assumed in this picture, and I assumed counterclockwise. So the reason I always show my moment vector in the picture going counterclockwise is so that I can still have positive representing counterclockwise and negative representing clockwise. Okay, so for part A, we now have an equivalent force coupled system acting at the point A. If you want all the action to happen at point A, but you still want this box to behave the same way as this box, you need that force in that moment applied at the point A. Now let's see part B. Says find the, or replace the force coupled system from part A with a single force and determine where it should be applied along the side labeled AB. So now what we want is we want to say, okay, let's take that picture. Actually, we could use the picture from the extreme left, or we could use the result that we just found in part A, because those two pictures are equal. So take either one of those, and we're going to say now it's equal to, here's our box again. We want a single force applied somewhere on the edge that's labeled AB, so that that one force, and that one force only, will have the same effect on the crate as the system of forces that we originally had at the beginning of the problem. So in other words, let's give our special point a name. I don't want to call it P, because P's already been used to represent the force down there. So let me just call it E, since we haven't. Let me just call it E, since we haven't used the letter E yet. So we have here, this would be F E X, and this would be F E Z. And what we need to know is the distance between the point E and the point A, perhaps. Okay, because it asks us to find two things. It asks us to find the force that we should apply to some point on the edge called AB. So, you know, B is the top corner up here. So I chose my point on that edge as the point E, and I'm going to apply some force that might have an X and a Z component, and I'm going to say that point E is located D meters away from point A on the edge. Okay, if I wanted to take the measurement from B, I could. It worked just as well. Okay, so like I said, this picture is equal to this picture, which is equal to this picture. So all three of these things are equivalent. So you could work with the first picture in this one, or you could work with the second picture in this one. It really doesn't matter. Okay? Why don't we work with the second picture, since it's maybe a little bit more simplified. So what that means is I've got to take the sum of the forces in any direction from this picture, set it equal to the sum of the forces in that direction in this picture. And then take the sum of the moments about any point in this picture from part A, set it equal to the sum of the moments about the same point in this picture that we have now for part B. So let's see how it looks. Let's take the sum of the forces in the X direction. Well, from the picture that we had in part A, I have FAX. And now in the picture that I have here for part B, I have FEX. Well, we solved already for FAX, it was 0. So 0 is equal to FEX. Take the sum of the forces in the Z direction. Well, we have FAZ from the picture in part A equal to FEZ in the picture we have now. Well, we already solved for FAZ, it was 240. So again, you combine the two components here, and what you're going to find is that FE is exactly the same as FA. It's 240 newtons going in the positive Z direction. And that should make sense, because what we're doing here, if you remember what I described before, is we're just taking the force that was applied at the point A, and we're just moving it to another point. So it's going to be the same force. Now the point that we're moving it to is going to be one where the moment that we add into the picture is going to cancel out the moment that we have in this picture, so that the end result is there's no more moment. Okay, just the fact that we're applying the force at a different point will create the rotation that we would get from either of those two pictures that we see before. So let's take the sum of the moments around some point now. I'll choose the point A. Seems like a logical point to choose. You could choose any point, it doesn't have to be A. But I choose the point A because, just like we had before, FAX, FAZ create no moments around the point A in this picture. So all I have is MA. Now in the right-hand picture, FEX creates no moment around A because its line of action goes through A. And actually its magnitude is 0, so you would end up with a 0 times 0 there. 0 magnitude, 0 distance, so you definitely get no moment there. Now FEZ, that will create a moment. Notice that's going to be counterclockwise, so it's going to be a positive. We're going to have here FEZ for the magnitude, and the perpendicular distance we call D. So MA from the picture that we have in part A, we determined to be 100 equal to FEZ, we determined to be 240. So if I want to solve for D, it's a simple division. D is equal to 100 divided by 240. If you divide it out, it's something about 0.42 meters. So FE, 240 newtons acting to the left, located 0.42 meters from A on the edge AB. So you apply that one force at that particular point, and that box will behave exactly the same way as the original box that had 3 people pushing on it with 3 different forces. Okay, so we started off with a box that had 3 people pushing 3 different forces. We reduced that to a single force and a single moment applied at the point A, and this box will behave exactly the same as this one. Okay, remember this moment vector that we have here represents a force couple, and essentially what you're saying, yes? No. Simplicity. So what happened, let's see, we have 3 forces from this picture, and in this picture, remember this moment represents a force couple. So here's essentially what happened. The force P stayed at the point A. Notice that F1 and F2 actually make up a force couple. The moment of that couple is actually what ended up here. Notice the distance between those 2 forces is 0.5. 200 times 0.5 gives us 100. And remember, that moment for that force couple is going to be the same no matter which point we choose. So if we applied it at point A, we're going to get that 100 Newton meter force couple here. Okay? If all we had was somebody pushing to the right, somebody pushing to the left, the box isn't going to translate, but it will rotate. Okay? That's what this moment captured. Okay? And then, of course, this third force would actually be the one that's causing some translation. But now what we're saying is, if we just take one person and apply a force of 240 to the left at this point, you'll still get the same translation in the rotation as you would with the 3 people from the beginning. So are there any questions about this one? This is number 85. So when it says find equivalent force couple system, that means you need to have 2 parts to your answer, a force and a moment vector. If it just says find a force, typically you're going to be finding the force along with some measurement of where it's located. Like in this case, we found the measurement of where it's located with respect to the point A.
Sir, on the second question, it said we all are applying force at point A, right?
Right.
But the force P has some effect on that particular moment, right? On question B, because we got a perpendicular distance and then we got a force going on Z direction.
So over here, right?
Yeah.
You're looking at this picture.
We got a force P 240 newton going on Z direction.
Oh,
right?
so you're saying the force P should have showed up in this equation over here? Okay, I was using this picture for the left-hand sides of my equations over here. I could have wrote the equations with the very original
but we
picture.
get the same result, right?
I could have used the original picture, wrote the same equations, and got the same result. So it would have looked like this in that case. So let's say we were working with the original picture, and we did the sum of the forces in the x direction. So 0 x direction, okay, equal to FEX. So same result that we got here. Sum of the forces in the z direction. So now you're going to have 240 minus 200 plus 200 equal to FEZ. So FEZ is 240. Okay, same result that we got here. Now, the moments, that's probably the one that's not as obvious to see what happens. So if we're taking around the point E, okay, so the point E is going to be located somewhere over here. And we said that the distance here was called D. So let's start with P. That's going to generate clockwise rotation. So there's going to be a minus term there, right? Mm-hmm. So you have minus P times D. Okay? Now, F1, let's see. I'm making some assumption, I guess, about where the point E is located. So if I'm holding the point, or if I'm putting the point E here, it looks like I'm going to be generating some distance counterclockwise. So I'm going to put a plus F1. Now, what's my distance here? From here, D minus 0.2.
Yes.
Okay. If I had assumed that the point E was down here, I would have generated clockwise. So I would have had a minus, and it would have been 0.2 minus D. So it would still be the same expression there. Okay, so where you assume point E is not going to affect your equation. And then for F2, given where I have assumed the point E here, let's say this is going to be counterclockwise. So I'm going to have another plus F2. And this is going to be this distance now, which is 0.7 minus D. Equal to, I have nothing around the point E in this picture. Okay? So 0. So I'm actually taking the sum of the moments around the point E, not A in this case. But you can plug the numbers in here. And what you're going to find is D still works out to 0.2. Okay, this is going to be negative 240D. This is going to be plus, this will be 200D. And 200 times negative 0.2, let's see, 40 minus 40. Plus 200 times 0.7, so that's plus 140. Minus 200D equal to 0. Okay, so what happens? 200D cancels out with minus 200D. Bring the minus 40 over and the 140 over, and what do you get? Negative 240D equals negative 100, so the minuses cancel, and D is still going to be 0.42 meters. Okay? So you could have used the very first picture. Now, look at the equation we ended up with here compared to the equation we ended up with here. Okay? It was a little bit easier to work with this picture because there's already a lot less happening in this picture. But you could go back to the original. You'll just do more work. Okay? Any other questions about 85? And I did, when I did the comparison between the first and the third pictures, I did the moments around the point E. You could have did the moments around point A, and you would get the same equation. Okay? Maybe the plus and minus signs would be different, but you would still get
so
the
we just
same
wanted
equation.
to prove that any point along AB, the moment going to be equal. for any point around.
Well, if you take this, you could take the sum of the moments around any point. You could take point C and find the sum of the moments around the point C. The sum of the moments around point C in this picture will be the same as the sum of the moments around point C in this picture will be the same as the sum of the moments around point C in this picture. Okay? So you can choose any point. It doesn't even have to be on the edge AB. Okay? Now they told us to find in this second part of the question, find a point on this edge where the force should be applied. So I knew that I was going to be somewhere on this edge, but I could still, for the equation, choose any point to take the moments about. Okay, we'll try 151. 3.151 is our next example. Still 2 dimensions. Okay, so here you see the rigid body that we have. We've got this bar AB has 3 forces applied to it as shown. And then at the end of the bar that we call A, there's some kind of gear there, and there might be a motor or something attached to that gear that's trying to cause rotation, make this rigid body rotate. And remember, rotation, the tendency to rotate, can be captured by a moment vector. So whatever the motor is or whatever's causing or wanting to cause the rotation in this rigid body, it's represented by that moment vector called M. Now remember, in reality, this M represents 2 forces, equal magnitude in opposite direction. So you might think about there really being 5 forces being applied. F1, F2, F3, and then somewhere on this rigid body, maybe it's here and maybe it's here, there's a force couple that has a moment vector that we have here M. Remember that force couple, whether it's applied here and here, whether it's applied here and here, as long as we have 2 forces equal magnitude, opposite direction, if we do F times D for the magnitude of one of those forces and D the perpendicular distance between their 2 lines of action, no matter which point we were to find the moment of that force couple, we would always get that same result. Well, they happen to show it down here at point A. So just remember that moment vector represents a force couple that's applied somewhere on this rigid body. And for those 2 forces in the force couple, if we found their moments about any point, we would always get the same result, and they've called that M. And they just happened to show it down here at the point A. They could have showed it at point B, though. Okay? And it would have been just the same. So here's our job. Our job is to figure out what should the magnitude of that moment vector be so that we can reduce this system of forces to an equivalent, a single equivalent force at A. And then we should find that force at A. So in other words, they want us to take this picture and they want us to set it equal to, here's the rigid body, here's the point A. They want us to find a single force at A where we might have some FAX and FAY components.